We usually think of fractions as simple descriptors of parts of a whole, like 1/2 or 3/4. But watch what happens when we take the denominator, break it open, and insert another fraction of the exact same shape inside it. We can do this again and again, creating a structure that cascades downward indefinitely. This is a continued fraction. It is built entirely on recursive thinking, where we apply the exact same replacement rule to the leftover part of the previous step, over and over. By continuously applying this single rule, a static number transforms into a dynamic, repeating process. This image displays the mechanical steps of that process. We start with 1/2. Then we replace that bottom 2 with 1 plus 1/2. In the next box, we take that new inner 2 and replace it again. To resolve these layers, we have to do the arithmetic from the inside out. In the second box, 1 plus 1/2 gives us 3/2. 1 divided by 3/2 flips the fraction, resulting in 2/3. In the third box, we repeat the process. Resolving the bottom layer gives us 5/3, which flips to 3/5. This table maps out the sequence of fractions that emerges: 1/2, 2/3, 3/5, 5/8, 8/13. These are Fibonacci numbers. Each new numerator and denominator is the sum of the two that came before it. If we track the decimal equivalents, the values start by bouncing around, from 0.5 up to 0.667, then down to 0.6 and up to 0.625. But as we calculate further steps, the size of those bounces shrinks, and the value settles closer to 0.618. Even though the visual structure grows more complicated with every step, the final numerical value converges on a stable, predictable point. If the replacement process never stops, we get an infinite continued fraction, which we can set equal to the variable x. Because this fraction goes downward forever, it is self-similar. The nested denominator inside the first fraction has the exact same infinite shape as the entire expression. It is a perfect copy of the whole. Since that nested portion is identical to our original x, we can substitute the variable right back into the denominator. This condenses an infinite visual structure into a simple algebraic equation, x equals 1 over 1 plus x. We can now solve for x using the quadratic formula. Multiplying through and rearranging the terms gives us x squared plus x minus 1 equals 0. The positive solution is exactly the square root of 5 minus 1, all divided by 2. This result, roughly 0.618, is the mathematical inverse of the golden ratio. By identifying the self-similar part of the infinite fraction, we can solve for its exact value without doing an infinite number of calculations. We can also work this process in reverse. Instead of evaluating an existing fraction, we can start with an irrational number, like the square root of 2, and build its infinite continued fraction from scratch. The first step is to isolate the whole number. The square root of 2 is approximately 1.414, so we split it into 1 plus the leftover fractional part, the square root of 2 minus 1. To rewrite that fractional part, we multiply it by its conjugate. This turns the messy decimal into a clean 1 in the numerator and shifts the square root into the denominator, giving us 1 over 1 plus the square root of 2. Notice that our new denominator now contains the square root of 2 once again. Pause the video here and try substituting our entire new expression into that specific spot. Performing that substitution gives you 1 plus 1 over 1 plus our new expression. The integers in the denominator combine to form a 2 plus pattern. As you repeat the substitution, that 2 plus pattern continues forever. Using a conjugate in this way forces a non-repeating irrational decimal to reveal its repeating internal structure. Consider the continued fraction defined by x equals 1 over 2 plus x. Try calculating the next few approximations to see where they converge. Then, use the self-similarity substitution to set up a quadratic equation and predict the exact value of this structure. You now have the two essential tools for navigating recursive math, using algebraic substitution to resolve an infinite staircase, and using conjugates to build one from a single number. Continued fractions demonstrate that even non-repeating, irrational values often hide an elegant internal symmetry. By finding the simple rule a number repeats within itself, we can map out and resolve structures that at first glance seem infinite.